So, I would like to talk some more about the traveling salesman problem. That's what we were doing last time. Traveling salesman problem. I hope you remember the basic setup here. That is, you have a graph with weights. So here is an example from last time that we did. A complete graph with weights. Remember, complete graph means that every edge possible is actually there in the graph. So every two vertices actually have an edge in the graph. And the edges have weights. So this was just one that we did at the end last time. The weights means individual numbers on each of the edges. And you think of these numbers as representing distances or costs or something like that. So to get from A to B, it's 3. To get from B to C, it's 4, and so on. And then your goal is to find the Hamilton circuit with least weight sum. The idea is you want to visit start, for instance, you could start at A and finish at A, and you want to visit each of the other 3 places using the smallest total weight. And, this comes up all the time in real life, like my somewhat, realistic example last time of me trying to visit all of my family members. It comes up in a serious way for like the Amazon delivery trucks or something, people who have to visit a bunch of places and they want to do so in the best possible ordering, but it's not easy to tell what order to visit them in. And last time we talked about, we did what I called the brute force method. The brute force method is just to write down all the possible ways of doing it and then add up the weights for each. So I would go something like, I could do A, B, C, D, A. I could also do I'm not going to do all the details because it takes a while, but I could also do A, B, D, C, A, etc., 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 and then find the weights of each. All right. This is not so difficult to do by hand if you are doing it for only 4 vertices like this graph here. But this is a in terms of real life applications of the traveling salesman problem, this is an unrealistically small example. A more realistic example would be like the guy delivering packages has to visit 100 places every day, and you need to be able to do that for 100 different vertices. So I will say this requires many steps, many like individual items in this list here. All right, now if there's only 4 vertices, there are 6 of them, which is not so bad. But if there's 5, there are 24 of them, and it quickly gets bigger and bigger and bigger. This requires many steps, and if you care to know about the details, for n vertices, we need a list of, there's a formula for this, which I don't need to get into, but n minus 1 factorial. I don't know if you've ever seen that exclamation point in math. That is actually an operation, which is called the factorial operation. And it involves multiplying together all the numbers, 1 times 2 times 3 times 4, up all the way up to, in this case, n minus 1. This is a very big number. So like for, say, 10 vertices, it's 9 factorial, which I plugged this into a calculator. Most calculators don't even have a factorial button because the answers are so big, but this is 362,880. So if you had 10 vertices instead of 4 vertices, there are 6 of them, which is not a big deal. But if you had 10 vertices, it's this many, 300,000. And if you had 100 vertices, it would be like some outrageously big number. Way too big, certainly way too big to do by hand, but even using a computer, these numbers are too big to handle. So even with computers, something like n equals 100 is unworkable. All right, but that is that is sort of like a realistic figure for instance, one of these package delivery trucks. I keep using that example, but there are many other places where this comes up. N equals 100. I wrote in. I meant is unworkable. This is why we're going to talk about other methods for doing this. So the fact of the matter is the brute force algorithm, which we talked about last time, is not practical for solving the traveling salesman at large scales. The scales at which people in real life need to do this, actually you can't use the brute force algorithm. Even if you're doing it using a computer, the algorithm is just too slow. It takes way too many steps. It might take you, with 100 vertices, it might take you like a few days to calculate the answer using a computer. And this is not good enough for the package truck guy because he needs to do it every day, right? And if it takes you a few days to even calculate the route, then you're in bad shape. All right, so we are going to talk about two other methods for doing this. But something interesting, though, is that actually no faster procedure is known. And this is, you could say, this is like one of the major unsolved problems in mathematics, or people would classify this as more of a computer science problem. Can you design a faster procedure than the brute force which gives you the correct answer every time? And actually this is something that people are working on, but it's not known. If somebody figured out a faster procedure, this would immediately affect a lot of the way that people do stuff in the real world. No faster procedure is known, I will say, which gives the best answer every time. Remember, we're looking for the best route, which takes the least amount of cost or distance or whatever. No faster procedure is known which gives the best answer every time. So what do people do in real life, since actually it is not possible to solve the traveling salesman problem in reasonable amount of time? We have what we call approximate algorithms. So we use what are called approximate algorithms. That is, these are methods which don't necessarily give you the best answer, but they're a lot faster. And that's what people do in real life. Like the package guy who delivers, 100 packages every day. Actually, that guy is not driving the mathematically best route because it's not possible to calculate that in time for him to, do his job every day. Instead, he's driving what is not necessarily mathematically the best route, but it's sort of a pretty good route based on these approximate algorithms. We use approximate algorithms which give pretty good routes, usually not necessarily the best. All right? And this is even true of like the GPS lady who gives you driving directions. Those directions are usually pretty good, but they are not actually the mathematically perfect route because calculating the mathematically perfect route is not reasonable to do within the time frame that you want it. Like when you're using your GPS, you want it to immediately start giving you directions. It doesn't really have time to calculate the absolute perfect route, and it doesn't really matter anyway because you don't necessarily need the absolute perfect route. You just need one that's pretty good or close to perfect. All right, so anyway, we are going to use these kinds of algorithms to give you pretty good answers. We're going to talk about two of them, and let's do one today, and we'll do another one next time. And this you'll see on your big checklist of topics. This is called the nearest neighbor algorithm. And I'm going to write NN for nearest neighbor. All right? This is a way of finding a good route in one of these graphs without actually checking all of them. So it finds a pretty good route, I mean, usually. Without checking all of them. Because it doesn't check all of them, it means it doesn't always give you the best answer, but it gives you pretty good answers. And for most cases in real life, that's good enough. And it's much, much faster than the brute force, even when you're doing it by hand. So let's just try an example. It's very easy to describe how to do it. So I'm going to make another one of these weighted graphs. This one has 4 vertices, but actually the nearest neighbor is easy enough to do that you could do it easily for even 10 vertices. Just a pain to draw the pictures in that case. All right, here is my graph with weights. I hope you can all see the weights on the graph. Here is my weighted graph. And we are going to try to find a low weight Hamilton circuit using the nearest neighbor algorithm. All right, this is what I'm going to tell you. I mean, I didn't tell you what that is yet, but here's the idea. It's a very simple idea, and it's something that I think anybody would come up with on your own if you were really thinking about this. You choose some starting point. Let's say, I'll do it starting from A. You might as well, I mean, whatever. You got to just choose some place to start. And then you start here and go one step at a time, and you choose edges to make a Hamilton circuit as you go, and each time pick the lowest weight legal edge. So in this example, starting at A, you see there are 3 options of which edge I could choose. I have the 1, the 4, or the 5. Which one should I pick? I'm going to pick the 1 because that's what I said in the words over there. You choose your starting point. Each time you choose the cheapest legal edge. And from here, there are 3 legal edges. And I'm going to begin by picking the 1. So here, I'm going to say, maybe I'll just copy this down so we can still see it. I'll give a little narration here. But this is very straightforward once you're doing it. So I'm going to start at A and then pick A to B for 1 because 1 was the cheapest option. Out of my 3 choices here, I could have gone across the top, down the diagonal, down the left side. I go across the top because that's the cheapest so far. All right, and now I'm at B. Where do I go from B? I have 2 choices. We could go diagonally down to C, or I could go straight down to D. Again, I pick the cheapest of those options, which is diagonally down to C. So start at A, I pick A to B for 1, and then from B, now we pick B to C again for 1. So that would be this way, right? From there, I had 2 choices. I could go down the diagonal or straight down. We should go down the diagonal. All right? Now, from C, you have to be a little bit, the only thing that might come up, I mean, this is a very easy procedure to do. The only thing that might come up is just you have to be careful about I said the rule was each time you pick the cheapest legal edge. Now from C here, I look at 3 or 5. Actually, well, you should take the 3. Actually, the 5 is not even legal in this case, because if you take the 5, you would have finished your circuit early. That's a sub-circuit, which is not allowed. So from here, from the C, I should not go to A. I mean, that's because 5 is more than 3 anyway. I should go across to D. So now from C, pick the edge C to D for 3. And then from D, again, you have to pick a legal edge here. From D here, you might say my choices are 2 or 4, but actually don't do the 2 because that makes a 3-way intersection at B, which is not allowed in a Hamilton circuit. It also closes up a sub-circuit, which is not allowed. You must go across to A. So from D, actually there's only one legal move at this point. We just finish with D to A for 4. All right, so that goes back up like that. And so my final answer is it's A, B, C, D, A. And the total weight, if you care to count it up, the total weight would be, you just add these numbers up. 1, 1, 3, and 4, that's 9. All right, and this is my answer for finding the path, or finding the Hamilton circuit starting at A using the nearest neighbor. It's called the nearest neighbor because it's just like when you start at A, if you think of these 3 choices, 1, 4, and 5 as distances, you pick the nearest, which is the 1. That's the smallest distance. And from each point 1 to the next, you just make the best possible choice at each step. All right? And it turns out, actually, in this example, that really is the best Hamilton circuit, although you would have to check all the different Hamilton circuits in order to convince yourself of that. But in this case, this is actually the best way to do it. All right. This is the nearest neighbor algorithm. And check how many steps are necessary here. Actually, it's only basically, 4 steps, right? And that's because there are 4 vertices here. So if with n vertices, this requires basically just n steps. Here there were 4 vertices, and this was basically just 4 steps. This is far better than the brute force method. Remember I said before, that means like if you had 9 vertices, it would only take 9 steps. You could totally do that by hand. Whereas the brute force method requires, 300,000 steps for 9 vertices. You could never do that one by hand. But like on our test or something, it would be totally reasonable for me to ask you to do this with 9 vertices. All right. This is much faster than brute force. Of course, the downside is you don't always get the absolute best answer. So I have just an example to show how that can happen. Unfortunately, nearest neighbor doesn't always give the absolute best answer. For example, how about, here's another one. And here's my weights. 2, 1, 3, 1,000, 4, 5. All right. And let's do the nearest neighbor starting at A. The problem with the nearest neighbor in terms of getting the best answer every time, the problem is the nearest neighbor procedure never takes a big look at the whole graph. It just makes one decision at a time. And the reason that's not necessarily good is to me, looking at this graph as a whole, I'm just going to start at A, right? To me, it is obvious just by looking at everything, I want to avoid this edge A to C at all costs, right? Because I can see that this one is far worse than all of the other ones. So doing anything that involves A to C is definitely a bad idea. But you will see if you just do the nearest neighbor procedure, starting one choice after another, I choose from A. Where should I go next from A? B, C, or D? You look at your options and choose the cheapest one every time. What do you say? B, yeah. My choices from A are the 2, the 4, or the 1,000. So I take the 2. That's the cheapest. This is how we do the nearest neighbor. I do A to B for 2. All right, and then from B, so now I have taken this edge. From B, I could do the 1 down or the 5 diagonal. I'm going to do the 1 because that, again, is the cheapest at this moment. So from B, I do B to D for 1. And now maybe you can see what's going to happen. At this point, actually, we can't go back to A because that makes a subcircuit, so we have to go across to C. And then the only way to finish will be to take the 1,000, which is a bad idea, but that's sort of what happens when we're doing the nearest neighbor. So from D, I go D to C for 3, and then from C, I have to go C to A for 1,000. All right? Just because by the time you get to C, there's no other way to finish at that point. So what the nearest neighbor is kind of like just doing one step at a time, doing what seems to be the best choice at that one step without ever taking a large-scale view of the whole picture, all right? This is like a, life advice. Usually in life, it's okay to just like do the next easiest thing with every single step. But sometimes you got to step back and think about your future a little bit and maybe do some hard things at the beginning to avoid hard things in your future. The nearest neighbor doesn't do that very well because here it is not able to kind of avoid the 1,000. So anyway, here, this time, the nearest neighbor gave a bad result, right? A, B, D, C, A in this example is not a good solution. It would have been better to go across those diagonals to avoid the heavy edge on the left side, all right? But I'll just say, usually it's pretty good. But this is just a little sort of warning when doing the nearest neighbor. Sometimes you can actually get quite bad answers. Usually it's pretty good, and that's why it is useful. All right, so I got some for you all to try. This is kind of a big one. This is 5 vertices, which I didn't want to draw and make you copy down, so I printed them out for you. We got 2 sides, but they're the same on both sides. I'm going to have you do something else on the back. Friends are going to be upset they missed this great handout. All right, so, it now occurs to me that I don't have this thing on my iPad. I'm just going to take a picture of it right now. I have one that I wrote on. Sorry about this. And I'm going to drop it. Drop. Okay, so what I would like you to do is, I suppose I could have told you what to do first and then done this while you're all waiting. Your job here is find the a Hamilton circuit using the nearest neighbor starting at A. Just what we've been doing. If you know what you're doing, this will only take you like 30 seconds or so, but try it out. I will come around and see how everybody feels. Unfortunately, if you make the wrong choice at the beginning, it screws you up for the whole rest of it. But I hope everybody feels like this is not hard to do. You just gotta make sure you don't choose it wrong. Here you go. I'll give you one more moment. All right, can we talk about these? There's not a lot to it. From A, you just have to make sure you pick the cheapest option every time. There are 4 options here. I have a 5, a 3, a 1, or a 7. You should take the 1 first, maybe just to avoid scribbling on the picture over there. I'm gonna take the 1 first, right? That was a 1. From A to D. Then what's next? From D now, my choices are here, 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 right? I could go 2, 5, or 4. I should take the 2. All right, so I'm going to go D to B next. From B now, my choices are 5, 3, 2, or 1. I already used this 2. I believe the 1 is the best choice at this point from B. So I should go B down to C for 1. Right? I hope everybody's making the same choices as I did. And now C, we must now go to E. You should not go from C to A because that closes up the circuit too soon. Your Hamilton circuit must visit every vertex, right? So from C now, you know, my choices are I could go, I guess the edges I didn't use 3 or 4 or 5 or something. It's got to be the 4 though, right? Because you may not finish too early. I have to go C to E. And then E to A to finish it off. All right? I hope that's what you all said. So if I were to write this in order, it's A, D, B, C, E, A. All right. And if you want, you could add up the weights for that. I'm not sure I did. I did. This is weight 17. If you add up the numbers along the way there. All right, this is the nearest neighbor algorithm. Anybody got questions about that? I hope that it seems fairly easy to do. I think it's easy to do. Like I said, the nearest neighbor does not always give you the absolute best answer. Another weird thing about the nearest neighbor algorithm, I think I can get rid of this. Another weird thing about it is actually nearest neighbor depends on your choice of starting point. This is another kind of oddity to this method. For example, if I look at, here's another 4-point example. 1, 1, 2, 3, 5, 4. I think this is the same as one that we did earlier. All right. In this case, if I start at A, I'm going to do this several times, seeing what happens if we start at various different points. All right, so starting at A, rather than scribbling on the original picture, just because I'm going to do this several times, I'm going to kind of make a little picture on the side. You don't have to recopy all the lines and numbers and such. But if I were to start at A in this example, you should go across the top for 1 first, and then from B, I did this 1. Now I should do this 1. That again is the cheapest option from B. And then from D, now I have to go to C because I can't finish and make a subcircuit early. I have to go to C and then A, right? So here my answer was A, B, D, C, C, A, all right? Okay, so this is the answer that you get if you are starting at A. What if I started at B? I am again going to write down the edges that I would pick starting at B. Now, starting at B, we actually have kind of a tie to begin with. Starting at B, I have a 1 or a 1. So the nearest neighbor says you just pick the cheapest edge every time. Now, if I was doing this on a test or something, I would make it so that there were no ties, so that you wouldn't, you would all get the same answer. But in this case, you can just kind of choose either one you like. Actually, in this example, it's not going to matter. But let's say that I decide to go to D first because of that tie there. And then from D, I could go up to A or across to C. What do you say? Which should I go next? I'm down here. Should we go across the bottom or up the side? Across the bottom. Yeah, your choices are 3 across the bottom or 5 up the side. So I should choose the 3. It's always the cheapest edge available. Now from here, you cannot go up to B because that makes a subcircuit. So I must go across to A and then back across to B. And actually, this is the same answer as this, right? They look different, but this is, I mean, B, D, C, A, B. This is basically the same as this one, all right? I'm writing the circuit in like a different ordering, but they are describing the same route through the graph, all right? Can we just look at what happens if I start at C now? I'm gonna copy this so I don't scroll it. What happens if we start at C? Starting at C, it'll say, I'm going to draw it again here, A, B, C, D. Okay, if I start at C, my choices from C are 2, 4, and 3. So I should pick the 2. That's the cheapest. Next, again, we have sort of a tie, 1 or 1. Let's just say we take the 1 across the top. Now from A, I can't go back to C because that makes a subcircuit, so I must go down to D and then D across to C. So my answer this time was C, B, A, D, C. All right, and this is different. Different from the answers that we got from the other two, right? So I'm just trying to demonstrate choosing a different starting point really can give you different answers when you're doing the nearest neighbor algorithm. This is slightly weird, but it does mean that we get sort of more options as far as what do we think the best Hamilton circuit is. It might be that, or it might be that. And this is actually the last, the last sort of thing I want to say today is a little variation on what we've done so far. We can say this in 15 minutes or less. So this is, let me just say, since different starting points give different answers, we can do what they call the repeated nearest neighbor algorithm. The repeated nearest neighbor algorithm. That is, you choose each different starting point and do the nearest neighbor starting there. right, so this involves doing it over and over again, although it's not that many times. If you have 5 different vertices, you do it 5 times, one for each different starting point. You do the nearest neighbor for each, and then choose the best overall. All right, so let's try that with on the back side of this paper that I handed out before. Can we try? Let's try the repeated nearest neighbor on this one. This is the one that I'm going to try and copy it from here. All right, let's try the nearest neighbor, the repeated nearest neighbor on this one. So that means you do the nearest neighbor several times with each different starting point. So I will just write down the first one, starting at A. Now, since you're going to do this, you're going to do it 5 times, right? Starting at A, starting at B, starting at C, etc. I would recommend you don't scribble on top of the picture here. So if you like, do like I did. So I will just not draw the whole picture again, but just draw the vertices. And this is what we already did, a few minutes ago. I had you do. Starting at A, you would go down to D for 1, D across to B for 2, and then B down to C for 1, C back up to E for 4, and then E back to A for 7. All right. And this one, I got A, D, B, C, E, A, and the weights are 1 plus 2 plus 1 plus 4 plus 7, which is whatever that is. 15? I think that's right. Yes, I think that's right. All right, so that's what we get when we start at A. Do it also, so the next thing you would do would be starting at B. Do the same thing, right? And then C and D and E. And then overall, we want to find the best of all of these. So I got 15. I don't know how good that is, right? The other ones might give you different answers, and you pick the best one overall. See what you think. I'll let you try the others. All right, can we talk about these? I don't know if everybody's totally finished. This will take you a few minutes to do, but I hope you are getting the feel for it. It's not really a difficult procedure to do. When I did, starting at B, I got this one, which I think I saw pretty much everybody came up with this general shape here. And those I added up and I got 12 for the total weights for this one, starting at B. Starting at C, I got this arrangement. Anybody agree or disagree? I think I saw people getting the same answer. It's also easy to mess it up, so I may have messed it up. But anyway, this one, I added up the weights and I got 15. I should have written a C there, right? 15 for that one. And then starting at D, I got this one. This was starting at D. Actually, this one is the same path as this one here, right? If you just look at the shape of it, it's the same. This one I wrote as starting at D, and this one starts at B. But here it was D, A, C, B, E, D. All right, and this one is also a 12 because it's the same as that one that I got from before. Anybody agree or disagree with my paths? I hope that we should be getting the same answers every time if I did it right, although it's easy to mess it up. And then finally, let's just do the one at E. It says A at the top, B, C, D, E. So I'm looking at my numbers here. If I start at E, we should do first, it looks like a 3 going across to B, right? And then from B, I should take the 1 here. From there, I should take this 3, and then I have to go here and here. This, again, is that same old path that you can still see at the top of the screen now. This was E, B, C, A, D, E. And this one, because it's the same as that other one, must also add up to 12. I stopped writing the numbers. This is a 1 and a 4. All right. Any thoughts about that one? So, what's my best answer overall? It's I had some 12s and a 15. I had 2 15s, I guess, and the rest 12s. And so the 12 is the better. Now, I said try the repeated nearest neighbor. So the best that we can find overall, the best was weight 12. All right, now you could write your answer in any way you like, and it might be that when I ask the question, I might tell you to write the answer in a particular way. What if I said, write the answer as a circuit starting at A? This can seem a little confusing if I ask the question like this, but certainly I could ask you the question. Write the answer as a circuit starting at A. Now, in this example, when you actually did start at A, you got this one for 15, which was not the best one. The best one was this one for 12, right? And so I am going to write this particular path as a circuit starting and ending at A. So writing this one, but start and end at A. That would look like A. Now there's kind of 2 ways around. You could go A to C first and around that way, or you could go A to D first and around that way, and it doesn't matter. They both have 12, so I will go down to C first. A, C, B, E, D, A. All right? If I say write the answer as a circuit starting at A, it doesn't mean use the one that you got when you started at A, because that one actually was not the best one. It just means take your best one and redraw this path or rewrite this path as if you were starting at A, and then you go through the rest of it. All right.